Well, the rules of the game are so simple. You simply fill in all the squares in the grid so that each row, column, and each of the 2 by 2 squares contains all the digits from 1 to 4 without repeats or omissions. So at the end, the problem, as you may know, is as follows. I will have an input matrix with some empty spaces in here, some empty cells, and the objective of the problem is to fill up with this all empty spaces with numbers from 1 to 4 with absolutely no repeats in each column, each row, and each 2 by 2 square. So the question is, can it be translated into a binary optimization problem? The answer is yes, and I'm gonna show you how. First of all, we're gonna discuss about how does MATLAB index a matrix. First of all, here we have a 16 element matrix, as you can see, 4 rows, 4 columns. Well, the filling numbers are 0, 1, 2, that doesn't matter now at this moment, but pay attention. We have this matrix M with all these numbers, and there is a MATLAB function called find.m that finds what I have written here as an input argument. Here we will find all the elements, all the indices in M that are equal, which contents are equal to 2. So as you can see here, I have this equal to 2 and this equal to 2. So it's first row, third column, fourth row, fourth column. So when I ask MATLAB find all those elements within the matrix M that have a value of 2, MATLAB returns row 1, column 3, row 4, column 4. But there is an alternative way to use this find.m. It's the following. When I ask where M is equal to 2, where the elements of M are equal to 2, here and here is the same matrix than before. Pay attention that when the output argument is a single argument, MATLAB returns the indices in the matrix. What do I mean? Here we have the first element, the second, the third, the fourth, the fifth, the sixth, till the 16th. So MATLAB returns the 9th element and the 16th element, as you can see here. So I'm going to use this way, the function find, in order to translate this problem into a binary optimization problem, and you will see. First of all, I built a function with the input argument being min. So min will be this matrix, well, this matrix or another one, it doesn't matter, with the empty cells like, for example, zeros, infinite, negative numbers, whatever, but not 1, 2, 3, and 4. What about the optimization array of this binary optimization problem? Well, we have 64 elements. Why 64? Because I have 4 numbers, 1, 2, 3, 4, and as you can see here, 16 positions. So that's why 4 multiplied by 16, it's 64 elements. What does x1 mean? x1 means to put number 1 in position 1. As you remember, every element in the optimization array can have a value of false, true. We don't know at the beginning, but at the end of the problem, we will know it thanks to the solution. As you can see, x2 means number 1 in position 2. That's position 2. This is position 1, 2, 3, 4, and so on till 16, as you may remember from the previous slide. And for example, x64 means number 4 in the last position. What about the cost function? We have no best solution. Why? Because we don't have any preference to put the numbers in a specific cell, empty cell. So the cost function will be ones. So all the elements in the optimization array will contribute the same value to the solution. Let's go to the complex part of the problem, the constraints. You will see that all the constraints within this problem are equality constraints. And you will see. We're gonna kick off with first the values that are already known. First of all, I find all the elements in the matrix that are equal to 1, 2, 3, and 4. And I keep these positions in 4 variables with names where are the and every number. Then I check how many numbers are not present, thanks to the function isEmpty. Because if there is no 1 in the matrix M this where are the ones, this variable will be empty, because there will be no positions for a number equal to 1. So isEmpty will be true, and this will be a 1. So if I do the addition, can you see here, of all the isEmpty with these variables as an input argument, I will have here the numbers that are not present. How many numbers are not present? I will not know if 1 is not present, maybe 2 is not present, maybe 3, 4, or any combination of them. I will not know which number is not present, but the important thing you will see is not which number is not present, but how many numbers are not present in the matrix. So, if numbers not present is equal to 4, means that the matrix is empty. So absolutely no constraints about numbers that are previously fixed to one position. But if number not present is not equal to 4, means that some of these numbers, maybe all of them, needs to be fixed at the beginning, need to be forced at some positions. So, first of all, I define the equality constraints for this part of the problem, the values that are already known. So I tell this matrices A equal equality. Remember that A equal 0 multiplied by X must be equal to B equality 0. That's how MATLAB understands this formulation. So how many equality constraints these previous values bring to me? So as you can see here, it's 4, because we have 4 numbers that are candidates to be fixed, minus the numbers that are not present. And then 64 columns means that this matrix have 64 columns because the optimization array has 64 rows. So then, first of all, I check if who is empty is where are the ones. That means that where are the ones, because I put a negative in here, that means that where are the ones is not empty. So then, this brings to me the first constraint. I state that the first equation, because k is equal to 1, so the first equation and these columns of the optimization array, where are the ones, have a coefficient of 1. And then, so we have a equality equal to zeros and will be ones in those positions where I have an already known number 1 in the original matrix. And at the end, because I know how many positions do I have in where are the ones, B equality, this element in here, the first element in this array, will be the length of the indices where are the ones. Because if I have 3 indices, means that there are 3 ones in the original matrix. So that's why I use the length. I increase k in order to check, to go to the next section that does the same but with the 2's, the same with the 3's, and the same with the 4's. And obviously, because I have a flow control by means of if and, if is empty, where are the 2's, this condition will not be accomplished. So I will manage the flow control of this constraint generation by means of the contents of every array that gathers the indices of the 1's, 2's, 3's, and 4's that I know at the beginning. Let's go now for the second set of equality constraints. They deal with the rows. I want a single number 1 in this row. The same goes for the second row, for the third, and for the fourth. And then I repeat this operation for number 2, 3, and 4. So that's why I have 16 additional constraints, equality constraints. So now these are A equality, B equality 1. So A equality 1 multiplied by the optimization array will be equal to B equality 1. So then, how can I write down this? First of all, as you can see here, I have the first position for number 1, the fifth position for number 1, the 9th position of the optimization array for number 1, and the 13th position of the optimization array for number 1 in this position. So that's why I'm writing the first inequality like 0. I will tell you later about this 0. And then I have 1, and I'm moving 4 units, 1, 5, 9, 13. Here we are, equal to 1. So that means x1 plus x5 plus x9 plus x13 must be equal to 1. So B equality, that's why it's 1. What about the second inequality? It's the same, but moving 1 unit. That's why before I had 0 plus, now I have 1 plus. For the third inequality I have 1 plus 2. That's why I put this number here. But the array, as you can see, is always the same. And these are the 4 constraints for number 1. The next ones, the next 4, will be for number 2. The next 4 for number 3. And the last group of 4 equality constraints will be for number 4. What's the difference? As you can see, 0, 1, 2, 3, 0, 1, 2, 3, the same here and here. But for the second set, I add a 16. Why? Because from x1 till x16, these elements in the optimization array, all of them belong to number 1 in the final matrix. But from x17 till x32, they belong to number 2. So as you can see here, I have an addition of 16 positions in the optimization array. That's why I add 16. And then for number 3 will be from 33 till 48. So that's why I add 32, because 1 plus 32 is 33. And the last group of equality constraints is for number 4, and it's the same than number 1, but adding 48 positions. Then what about the columns? The columns is quite similar. I want a single one in here, a single one in here, the same goes this, and the same this, and the same goes for number 2, 3, and 4, so that's why I have 16 more equality constraints. But I call them A equality and B equality 2. It's quite similar to the previous situation, so I will go so fast in here. So as you can see, now the first, second till the 16th inequality, here I have from 1 to 4, so 1, 2, 3, and 4. Why? Because here I have 1, 2, 3, and 4 are consecutive numbers. And here I add a 0. But then for the second column, I add a 4. Why a 4? Because when you move to the right, you are adding 4 positions. When you move to the right, you add 4 positions more. So that's why 0 plus, 4 plus, 8 plus, 12 plus. So that first set of equality constraints go for number 1, this for number 2, this for number 3, and this for number 4. What's the difference? Because I add 16, 32, or 48 the same way I did for the row constraints. Now let's go for these squares. As you can see, their positions in the optimization array are 1, 2, 5, and 6. So that's why now the columns for every constraint in this third set of constraints will be 1, 2, 5, and 6. And as you can see, I add 0 because 1, 2, 5, and 6 is for the first square. But then I add 2, 8, and 10. Why do I do this? Because for the next square is 1 plus 2. For the third square is 1 plus 8 in order to become a 9. And the last 1 plus 10 equals to 11 for this square. But this is for number 1. What about number 2? What about number 3 and 4? I add 16, 32, and 48 as before. What about the most common constraints in our problems? Every number must be assigned 4 times. 1 in here, 2, 3, and 4. 1 in this column, 2, 3, and 4 times. 1 in this row, 1, 2, 3, and 4 times. So a number must be assigned 4 times. 1 per row, column, and group of 4 cells. So that's why I do the following. All the elements in the optimization array that belong to number 1, the first equation is for number 1, must be equal to 4, as you can see here, because I must assign every number 4 times. The second equality constraint, all of them are equality constraints, is for number 2. That's why I add 16 as before. Here 32 and 48 because I'm talking about number 3 and 4. What about the other way round? Every cell must receive a single number. Well, here, because I have 16 cells, that's why I have a 16 here. So I have 16 additional equality constraints. Pay attention that here what I'm doing is the following. The first one is about the first position, the first cell here. As you can see here, that's for number 1 because x1 is number 1 in position 1, but then x17 is number 2 in position 1, and as you can see here, I add 16 positions. That's why this array is increasing by 16 units every time. What about the second equality constraint? I add a number 1. Why? Because the second position is this, and it's number 2. So that's why I add 1 unit for the column of the optimization array. I keep on going this way until the last, that is adding 15 in order to have 1 plus 15, 16. Finally, I do the constraint compilation. First of all, if numbers not present in the original matrix are equal to 4, so it's empty, there is no need to force any number at the beginning. So as you can see here, the group 0 of equality constraints are not present. But if there is any number present, 1, 2, 3 or 4 numbers present, then these equality constraints must be present because the algorithm is expected to force some numbers at the beginning. Then I call the optimizer, int_limprog. C, remember, it's full of 1s. 1 to 64 because from x1 till x64 all of them are integers, integer numbers. Then here pay attention to empty matrices. Why? Because we don't have inequality constraints. We do not have this. So that's why these two input arguments are empty matrices. Then the A equality, B equality, can you see here? They are all stacked together. And then these are the lower bounds and the upper bounds. Why? Because this ensures that the solution is composed by integer numbers, but as you may know, this must be false or true. So that's why I put the lower bounds and the upper bounds for all the elements in the optimization array. Finally, this section is only for filling the empty cells of the matrix, of the SUDOKU matrix, with the solution. The positions to B1, to B2, to B3, and to B4 are in the optimization array, are in the solution for the optimization array. And then finally, I assigned them in the output matrix. Well, here you have some examples. As you can see here, I have a lot of empty cells in here, and they are filled, as you can see, with the optimum numbers. Here, a 2 and 3 are missing, so the algorithm decides to put them this way, and here a 2 and a 3 are also missing, but you cannot put 2 and 3 because you would repeat this, so that's why they have been exchanged. Well, you can check. Then here we have a nearly empty matrix. There is a lot of freedom for the algorithm here to decide, and the solution, as can you see, is a combination of 1, 2, 3, 4, but in different positions, as you can see here, but being respectful of the original numbers, as you can see here. They are kept on the solution. Then I have 1, 2, 3, 4 this way, as you can see, 1, 2, 3, and 4 from the original one. Then, for example, here, only a 4 is missing here, and the algorithm success on it. So here is a 4. Here, a 2 is missing, as you can see, 3, 1, 3, 4, 1. A 2 is missing, and the algorithm success. Then here we have all the numbers, but 4 is not present, and the algorithm success with this solution.